Hey, what's up, guys? This is Chung here, and this time let's continue on this on our tree journey here. So today we're gonna talk about this number 958. Check completeness of a binary tree. So for those who doesn't know what the bi complete binary tree is so a complete binary tree on the if it's not the last level, all the nodes has to be filled. And you're only allowed to have a missing node on the last level, and but you're only allowed to but on the left side, the missing node on the left side of the missing node, all the nodes have to be filled. Uh, yeah, have to be filled. Basically, you need to have the last nodes, all the nodes filled as as left as possible. Yeah. For example, here there's a 7 here, but a 7 here, but you have a missing node here. This is not allowed, right? You can only allow to have one missing node on the right side. And so how do we do it? I mean, there are like I think many ways of doing this problem. So the first one is to you can keep counting the index of each node, right? So for example, this one has the index 1, right? 1, 2, 3, 4, 5, 6. Yeah, basically the same thing here. And you just have an array here. You have an array to store all the indexes here, all the index in this tree, right? And remember, you have to do a breadth level search, which is the level order traverse. So you need to have one here, two. Remember, this is the index, right? Three, four, and to the end, to the six, right? And in the end, you just check if the last index is equal to the length of this array, right? If it's the same, then it's a complete binary tree. If it's not, for example, this one, 1, 2, 3, 4, 3, 1, 2, 3, 4, 5, and the last index in this array will be 7, right? It will not be 6. Then it's not. Then it's not the length of the right. And how can we check each of the node index here? So basically we start from root node 1, right? Start from root node 1, and every time when we see a node here, we just use the current index times 2 times 2 equals to the left the left sub the left node, and then current index times 2 plus 1 to the to the right to the right node, right? And then we just keep traversing for the whole tree. In the end, we just do this comparison. Yeah, that's obviously a time complexity and the ON space complexity, right? And that's one way. The other ways is that we can like most likely we would be able to stop the traverse earlier, right? How, right? So if you watch closely, every time if we see a gap and there is like another node after this gap, then we know this is not like a complete binary tree, right? Because like remember we're doing the other level traverse. So we do 1, 2, 3, no gap, right? 4, 5, no gap. 6, no gap. See, there's no gap until uh we traverse all the complete tree here. For example, this one, 1, 2, 3, 4, 5. There's a 6 here, right? Okay, we saw a gap and then we see another node, then we know it's not a complete tree, right? Another example would be like 1, 2, 3. Let's see, then 4, 5. Let's say there's a 6 here, right? And then we have some other nodes here. Let's say there's like 8, right? 9 and 10, right? So in this case, the last level it is fine because all the left side are filled. But on the previous level, there's a gap here, right? But remember, we are doing this row level traverse. I'm sorry, the level order traverse here. So we're doing a 1, 2, 3, right? 4, 5, 6, and then when we try to find the right subtree here, it's nothing here. There's nothing here. Then we already know we already saw a gap here. And then once we reach this level, okay, we saw a gap. Then it's not a complete tree, complete binary tree, right? So that I think should be pretty clear what we need to do here, right? So first, just build a queue here to do the row level traverse, right? And then collections.dequeue, which push the root to it, right? Then we do a while queue, right? Because here we are doing the level auto traverse, but we don't care about what levels are we right now. We just care about if we have seen a gap before, so we don't need to create a level variable to keep track of the level, right? And we don't even need to do that uh, that for count to 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 traverse all the nodes on the same level here. We don't care. We just as long as we're following the same sequence, it's fine. Basically, the same sequence will be the node that will always pop from the left, right? The pop left, right here, and then we're also gonna see gap, right? False. So I'm gonna write this thing here. If node, right? So remember with a regular level order traverse, we usually do a check here. If node dot left is not empty, then we append to the queue, right? But keep in mind here, here we want this one to be, we want this node to be added to the queue so that when we traverse this level, we can see there's a gap, and then we can just keep doing, right? That's what we need to do here. We just do a like we just append without checking the existence of the node. Q dot append node left, right? And Q dot append node right. We append the left first and then right, so we can make sure, and we are popping from the left, so we're making sure we always traverse from left to right. Since we don't check that, we don't check the none here, we have to check it here, right? So if not, right, if not node, right, then we set a flag here. We seen gap, right, equals to true, right? Else, right? Else we do this, right? Let's see. If it's none, there won't be any left and right here. But if there's not none, first we set this gap here. Remember? So and this time inside the if here, if, right? The else means okay, we see another node here. But if we have seen the gap before, right? If we have seen the gap before and we see another node, what does it mean? False, right? Right, false. Then we just keep doing it. In the end, if everything works fine, then we just return true. Yeah. Yeah, I think that's pretty much it is. Okay, let's try to run it. True. Perfect. Cool. All right. I think it's kind of pretty straightforward. So we just keep pushing the left and the right node, right? Regardless of if it's a null or not, because we do a check here. If it's a null here, we set the flag here. And if there's a And if it's a node, valid node, and we have seen a gap before, we know it's not a complete binary tree. Cool, guys. Okay, I think that's it. Thank you so much for watching the video. All right, I'll see you guys later. Bye.